Hot! Heat! How do things stay hot even after they begin cooling down? We'll start this off with something we all know, close and dear to our heart, the beginning of Earth's lifespan. So, Earth, in the beginning of its, creation, or birthing, was a molten rock of lava and magma and, liquefied heat stuff, right? And as time passed, the Earth began to cool down naturally, as all this stuff is surrounded by, an atmosphere of mostly carbon dioxide. It will begin cooling down because the air around it is cooler than the actual rock, the molten rock. So, how did the Earth continue staying hot after billions upon billions of years of heat being evaporated out into the atmosphere and cooling down? You see, the molten rock and, deep within the Earth's crust experiences something that we should all know. Something that is smaller will cool down much faster than something that is larger. Intuitively, a pea will cool down much faster than, say, a potato, which is why you cut a potato in half in order to cool it down. So think about it like this as well. A potato is mostly just hot on the inside, right? And the surface area, the potato shell, is just the stuff that is linked to the colder air that is, letting the heat dissipate through the air, which is cooler than the inside of the potato. So, if you cut a potato in half, the volume doesn't change. You're not taking out any mass or heat. You're not taking out any hot mass from the potato, but you are adding more surface area for which heat is able to escape from. So, basically, when you have, something that has a bunch of, a large amount of volume, but not a lot of surface area, it will naturally stay hotter for longer, since it doesn't have a lot of space to evaporate or dissipate from the heat. Now, why does this happen? Well, this is the math part, which is maybe boring, but if you'll bear with me. A cube that is 1 inch by 1 inch by 1 inch will have a side length of 1 inch, an area of 6, and a volume of 1. All of that comes from the side length just being 1. The area is 1 times 1, the face of a cube, multiplied by 6 sides. And the volume is just 1 times 1 times the third dimension, 1. So, when you double the side length, you have double the side length, naturally, obviously, which becomes 2, but the area, the surface area of the cube becomes 24, because it's 2 times 2, which is 4, times 6, which is 24. But if you looked at the volume, it will become 2 times 2 times 2. Once again, the third dimension multiplied by the area of the face, because again it's a cube. That'll become 8. Now notice the jump between the surface area to surface area and the volume to volume. The surface area to surface area was 6 to 24. That jump is only a factor of 4, right? But the jump in volume, 1 to 8, is 8 times the distance. If you continue doubling and doubling this cube until it's the size of the Earth, then the volume will greatly outpace the growth of the surface area, such that the volume will now have a smaller amount of area to have heat escape from. So, naturally, as the Earth is much larger and much larger than 1 inch, then it'll have a lot more surface area. It'll have a lot more volume and less surface area for heat to escape from it, which is actually interesting in that Mercury and Mars, or Mars specifically, was a lot like Earth in that, it had a lot of the same composition. It's dirty, it's, rocky and junk like that. Close enough-ish. It has an atmosphere that's akin to Earth, but it's slightly smaller, so that the volume of Mars could not keep up with the surface area. And that resulted, along with the atmosphere not having, greenhouse gases, was, not having greenhouse gases, that might be no, okay, that's besides the point. So, Mars is much smaller, so then you have, the heat and being able to escape the volume of Mars much faster. And, you know, all of that is why Mars is much cooler than Earth. In addition to maybe being a bit farther away, so, you know, but that's, anyways, all of that is an interesting little tidbit on heat and the square cube law, which is what I just described mathematically. But the bigger question is, how do you stay hot? You would know. I hope you have a wonderful week, and goodbye.